Okay, Kok Pao, I can see you.
Hello, doctor.
Okay.
Can you hear me?
Yes, very clear.
Okay, thank you.
Can you just try to share your PowerPoint or not? Do you know how to use this one or not? There's a
Yeah,
function
sure.
of
I know.
share content. Let's see, can we see your content or not? Just want to try and see everything working or not. Okay, you are sharing right now. Yes, I can
Yeah.
see it.
See?
Very nice, big. If
Okay.
you make me, if you press F5, okay, oh, very good. Can see everything.
Okay.
Oh, very nice. Let me see how to change this. Okay. So right now when you okay, can very nice lah. Good.
Okay.
So you just play around and see. You cannot see my face
Title,
properly. Yes.
online seminar form FYP2 stroke 4A.
Stu for EC online. Just put their name and then EC only lah. But I'll EC later lah. Hi Mastura, can you hear us now? This is Kok Pao here. Kok Pao dah showing the slide everything dah boleh. Tadi I already talk to Suhana. Okay, also okay, boleh. Audio everything is okay. Can you hear us or not? Alamak. See, Dr. Mastura cannot hear us. We had to see what's the problem. Because she cannot hear us. Hi, Fadli is here already.
Hello.
Hello. Dr. Mastura, di mana dia mute all entry. Memang tak boleh dengar ke?
Hello?
Yeah, boleh dengar dah?
Baru boleh.
Baru boleh Okay.
Okay.
Fadli, if you shy, you can just tutup your webcam dulu lah. Sebab you bukan nak present kan. So
Okay.
you can tutup, you nak buat apa, you buat dulu. Kita tengok Kok Pao dulu. He penting. He has to show his face.
Okay.
So everything is okay now. See, it's recording in progress. So Dr. Suhana, are you okay or not? If he start early, Kok Pao start early or not? He has 59 slide.
Wow.
I will try. I will try.
Let me put my timer. Lemak, where's my timer here? Timer 10 minute here. Okay, so Kok Pao, I think you can start first lah. Since you're already here, let's not waste the time. I'll set time minutes from here and you maximize it. Okay, all right. Okay, you can start now.
Okay. Good afternoon, Dr. Mastura, Dr. Maketa, and Dr. Suhana. My name is Hogopo. So today I'm going to present my FYP which titled Electrical Characterization for Junctionless Gate-All-Around MOSFET. And my supervisor is Dr. Muhammad Afiq Nuruddin. And this is my presentation outline for today. Figure 3 shows that the size of the transistor has been scaled down over the year. However, there are many problems has been recognized as the device continues scaling down. Short channel effect will occur when the channel length is comparable to the division layer width of the source and the drain. And the example of short channel effect are DIBL, surface scattering, higher leakage current, and quantum mechanics effect. There are many solutions to solve this issue. One of the potential solutions is junctionless GA MOSFET. Now here comes a question. Why I chose junctionless GA MOSFET? Junctionless nanowire transistor or JNT is a heavily doped silicon insulator nanowire without junction with a gate which wrap around to control current flow. JNT require a uniform and constant doping level throughout the device and typically range from 10 power 90 to 10 power 20. JNT make the fabrication process simple, exhibit low leakage current, and excellent short channel characteristic at shorter gate length. So the problem statement in this research are: how does the device parameter will affect the performance? Second, how does the electrical behavior of junctionless GA MOSFET? The objective of this research are to investigate the impact of the device parameter on the performance. Second, to study the electrical behavior of junctionless GA MOSFET for NMOS and PMOS. And the third one is to determine and characterize the best parameter combination for junctionless GA MOSFET in order to obtain better electrical performance. The first scope is electrical characterization, such as subthreshold swing, DIBL, threshold voltage, and current ratio. Characterization is targeted for submicron process node, such as gate length less than 100 nanometer, and the radius is between 2 nanometer to 10 nanometer. Second scope is the ticket simulation physical model, such as drift diffusion, constant mobility, Schottky rate for combination, recombination model. So let's move on to literature review. The table 1 shows that the performance analysis by applying different solutions which to solve the short channel effect. From the table, it can be explained that all the solution will provide a better uh, uh, better result, which will eventually help to reduce the short channel effect, which occur when a device is downsizing. And junctionless is getting popular for research study. So this table shows the performance of junctionless MOSFET at different structure. And one of the structure is a GA MOSFET. GA MOSFET is suitable to fabricate in junctionless as it turns off the device by creating a division region at outside with its gate. GA MOSFET will provide a better gate controllability and a low leakage current which will widely used in future. So that's why I chose GA MOSFET. After that, I summarize all these tables in table 3 and table 4. And all the authors mention about the doping level for channel, drain, and source, which must be the same and highly doped. Second is the better short channel characteristic. So it's the same. The overall project flow is from background study, then determine title, objective, and scope, literature review, construction of the device, then validation with the published paper, variation of the parameters, electrical characterization, after getting the result, comparing with published paper, and discussion and conclusion. So this is a validation process. First, I have to find a suitable published paper to validate, then extract the graph and the parameters used in the paper. Next is fix the parameters mentioned in the paper and the varies the parameter doesn't mention in the paper, such as length of source and drain and gate thickness. And finally, compare both graphs. So this is show the process of creating the junctionless GA MOSFET structure using TCAD software. First, determine the requirement for the design and parameter for the device. Then, define structure specification and material parameters such as electrode, mesh, and region. The solution is obtained using load, solve, and save. And the result is interpreted through Tony plot. So this is a structure in 3D, and this in 2D, which I cut in YZ plane. The first step is a silicon, then is a silicon oxide, polysilicon gate, and the source and drain at left and the right side, and finally conductor. So this shows how I extract the electrical parameters such as subthreshold swing, which is 1 over slope, current ratio, I on and I off. Next one is a VTH threshold voltage, and the last one is a DIBL, which is delta VTH over delta VD. Okay, so the result. So this table shows the parameter used in published paper and simulation for validation. So as you can see that all the parameters used are the same. And this is a structure in 2D. And finally, I compare both results and plotted on the same graph. The results between simulation and published paper are almost the same. After that, I analyze the electrical properties based on VTH, current ratio, and SS. First, I vary stopping level for NMOS and PMOS. In general, the doping level increase, VTH and current ratio will decrease, while the SS will remain constant. The purpose of this analysis is to know that the effect of the parameters on the electrical properties. Next, I tabulate the result in Minitab and plotted. The control graph is plotted. The purpose of the control graph is to know at which doping level will yield a better electrical performance. So next, I repeat the same for the gate length. When the gate length decreases, VTH and current ratio will decrease, while SS will increase. For radius, when the radius is increased, VTH and current ratio decrease, while the SS will remain unchanged. And finally, this table shows the best combination of the parameter used in this research for NMOS and PMOS. Doping level, gate length, and radius will change based on the control graph and the bar charts in the previous slide, while other parameters will remain unchanged. One of the suggestions of the application is inverter. So as you can see that my radius for the NMOS is half compared to the PMOS, while the mobility is double for the NMOS compared to PMOS. According to Baker 2019, for the device to be implemented as an inverter, radius for the NMOS must be 2 to 3 times smaller than the PMOS, while the mobility for the NMOS must be 2 to 3 times larger than the PMOS. And this is the IV characteristic based on the parameter used in the previous slide. After that, this shows how I extract the result for electrical characterization. First, a VTH 380 millivolt, and then current ratio 1.33 e power 7, SS 70 millivolt per decade, and DIBL 95.96 millivolt per volt. After that, I compare my result with other published work, and also my targeted value is based on IRDS 2018 G45M24 3 nanometer, not i5F3. And in overall, my result is better compared to other published work, especially for the current SS and DIBL. So next, I summarize a final result for electrical performance for this research for NMOS and PMOS. And in conclusion, for validation, the graph for selected published paper is extracted and the result between simulation and published paper are almost the same. The best combination of the device parameter were found, higher current ratio, better SS, and good DIBL were obtained, which can fulfill targeted value for low power logic. In future work, first I do apply the junctionless to other structure. Second, use lower dimension of gate length. Third, compact modeling of GA MOSFET for digital circuit implementation. And finally, is analyze CV properties of junctionless GA MOSFET. And this shows the timeline throughout my FYP. So next is a reference. And thank you. So that's all for me.
All right, thank you, Kau Pao.
Thank you.
In time, 10 minutes, very good. A lot of comprehensive result, everything you put it very nice. So now we're open for Q&A. Maybe I'll invite Dr. Suhana first to give comment.
Okay, Faha.
Hi, doctor.
I just have one short question.
Okay.
The theoretical study of a normal transistor is the same for junctionless transistor. The equation that governs the VTH and VTH.
Yeah. The extraction is all the same. Like ETH current ratio. The extraction is the same. So let me show.
So it uses the same equation as the normal transistor.
Sorry?
It follows the same equation as a normal transistor without the junction.
Yeah, it's the same. Because the junctionless is a main different is a topic level. The topic level must be the same for source train and channel. But the extraction like electrical characterization is the same, like VTH, current ratio, SS, and DIPL.
Yeah, extraction is the same, but how about the equation, the theoretical equation for VTH? You know, there's an equation, right, for transistor.
Yeah.
So it is the same, is it? You're saying?
Yeah, it's the same. But actually, I didn't more on the equation because I'm more into the simulation and then I extract out the result. But I have studied
Yes.
about the equation is the same.
Yeah. So for your report later, you need to back up with this theoretical study for your discussion.
Okay.
Because it lacks of discussion, why is it like this, why is it like that? Okay, because you are just like
Okay.
reporting the result, right? So in your
Okay.
thesis later on, back up more with the theoretical equation. Okay.
All right. Thank you, Dr. Suhana.
Okay, that's all.
Thank you.
Dr. Masura, you have any comments for Kok Pao? Oh, Dr. Masura. Hello, Dr. Masura. Not sure she can hear us or not. Huh?
Ding, 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 ding.
Can?
Okay. Sorry. Okay. The first question is, in the step, you mentioned that you extract the data reported by other researcher, right?
Uh-huh.
Can you briefly explain
Is it validation?
yeah, so that one is experimental or the simulation data as well?
Simulation. This
Simulation.
one. Yeah.
Or the published paper is also simulation.
Actually, it's published paper is simulation, and then the simulation for the ticket simulation is my result, and then I compare both.
Okay. So what's
This
the
is a
difference?
published paper.
Mm,
So I follow exactly the same that the parameters mentioned in the papers.
okay. So
Yeah.
what's the difference between this published paper and yours?
The exact difference is like this paper also using junctionless MOSFET, but
Uh-huh.
then it using the 1000 nanometer. After that, I reduced down to 20 nanometer, which is my final result is 20 nanometer. This is my final one. Get length 20 nanometer. Because nowadays, most of the MOSFET is less than 22 nanometer. So I try to reduce down the gate length and
Mm,
analyze the electrical properties.
okay. And you
Mm.
have compared your data, your result with others, and it's found that yours is better. Can you
Yeah.
clarify further about that one? In terms of what? That you say that yours
Right.
is better.
So actually, you can see for the current ratio, the targeted value is 1.271. So mine is 1.32, which
Mm,
is higher and fulfill the targeted. And compared to others, is 0.1 and 0.07, which is higher than that. For current ratio, higher is better. And,
mm,
and for the SS also, for the SS, 75 milliwatt per watt, and mine is 70, and compared to others is lower than that. For the DIBL is also for the targeted value is must be less than 100 milliwatt per watt, and
mm,
mine is 95. The reason is why I get too close is because I try to because you can see that my threshold voltage is a bit higher. So I try to reduce the VTH, but then the current ratio will be lower than the targeted value. So this is what I can get to fulfill the closer compared to a targeted value. Because when I reduce down the VTH, the current ratio will be reduced also.
all right. Okay.
Mm.
Thank you. That's all from me.
Thank you.
All right, Kok Pao. So you can say like a trade-off lah. Sometimes you say that if this increase, then this one a bit lower like that lor. That is called trade-off lah.
Yeah.
You
Oh,
can use
trade-off.
the term
Okay.
lah. You Google the term trade-off lah in your report later. Okay. Thank you,
Okay.
Kok Pao. So we proceed to the next one. Fadlin.
Okay.
Fadlin, can you just share your content or not? Kok Pao, you can over already. You can just close your video. It's okay. Okay. Alright. Okay, Fadlin. Kita tengok macam mana. Your one can share not the
Okay.
content.
So give me time to fill up the marks for Hokopao.
Oh, you need times to fill up Okay, boleh. In the meantime, you fill up, kita set up dululah for Fadlin. Fadlin, you can set up dulu tak? Tengok tak boleh share ke?
Set up dulu tak apa.
Okay, wait.
Tak apa, dia ada kat share content. You have to go to your Webex and share content. Sini betul. Tapi tak nampak apa lagi lah. Dia maybe internet slow bit lah. Starting to share content. Oh, kita dah nampak yang ni. Okay. How about your webcam pun kena on lah. Nak tengok muka eye contact
Alright.
lah. Dah hilang dah.
Wait a second.
Sekarang tak nampak apa pun. Nampak hitam.
Wait. Okay.
Oh, sekarang nampak your face. Then the
Wait.
content dah hilang. Okay. Kita tengok.
Okay, kejap.
Sekejap internet dia nak tengah loading ni.
Okay. Can you see?
Okay, I can see your slide.
Okay. You boleh press F5 bagi besarkan yang presenter mode yang slide. Yang ni. Okay. Kita tengok dulu. So Kok Pao, I think if you're done, I think you can leave already lah. If you want to stay, you can stay lah. Because there's nothing ready for you. Demo also tak payah demo. We look at your video ni. Okay, so Kok Pao, if you want to leave, you are welcome to leave lah. Not you have to stay here for 2 hours Fadlin. So Dr. Mastura, okay, all done Boleh dah bagi markah ke? Need some time.
Dah. I'm done. Okay.
Okay, done Okay.
Alright.
Okay, Fadlin, you can start now Let me set the timer 10 minit lah Okay, you may start now. Thank you.
Okay. Can everyone hear me clearly?
Yes,
Hello?
boleh. Clearly, boleh dengar. Saya boleh dengar.
Okay. Alright. Hello. Good morning. Good afternoon to everyone. My name is Nurfadin Izzati binti Zaihan. My final year project is about electrical performance of multi-wall carbon nanotube to study the effect of tunneling distance between CNT and CNT. I am under supervision of Dr. Nur Izaila binti Alias. So this is my outline. Next is my project background. So first we need to understand there are two types of tunneling. There are classical mechanics tunneling and also quantum mechanics tunneling. So in my project, I'll be focusing on the quantum mechanics tunneling that describe the existence of transmission even when the energy is lower than the potential barrier. So next there are two types of level of research that determine the conductivity of nanocomposite. There are macroscopic level of research and a microscopic level of research. So to understand macroscopic level of research is looking at it in a collection of CNTs. However, microscopic level of research is more on the atomic level. So and then there are a few examples of macroscopic level of research where they investigate the enhancement of mechanical, electrical, and thermal properties. And other than that, they also increase the amount of fillers, and then they increase the to see if the effect to the conductivity. So this is the few example of the macroscopic level of research. So the problem right now is that there is a limited exploration on the microscopic level of studies, especially on the interaction of two close CNT. So this is a few of types of microscopic level of studies. So the importance of microscopic level of studies is that
Alamak.
it also affect the performance, especially the conductivity of dry electrode that consists of PDMS and multi-wall carbon nanotube. Yes, multi-wall carbon nanotube. So my objective is to first compare the design structure and electrical properties of single wall and multi-wall carbon nanotube, and then to study the effect of tunneling and the electrical performance of multi-wall carbon nanotube. So my literature review, I'll be focusing on this part, which is the literature review summary, and I'll be talking about the shortcoming of each literature review that I have done. So for first literature, it only focus on the electrical properties and application of CNT. So it lacks in explanation of CNT's interaction. And then the second literature is more onto the macroscopic level of research. That is also the same for the third literature, but it is focusing on the mathematical modeling. And then for the last literature, it talk about the tunneling between two material, gold and single wall carbon nanotube. However, it manipulate the diameter of CNT. So based on that, my methodology is first, we need to understand that there are two types of structure that I did. First is bulk. So this simulation I use quantum wise. So first I do bulk simulation and then a device structure. So the difference between this structure is the device one has electrode potential and also gate potential. So from there I simulate the transmission spectrum, then simulate the transmission spectrum of device, and then from there I compare between the bulk and the device transmission spectrum. So if it is equal, what I did is I complete all of the simulation for single wall carbon nanotube to understand the electrical performance. And then I manipulate the gap distance from 0.3 nanometer and 0.6 nanometer. So the complete simulation is first looking at the transmission spectrum, electrostatic difference potential, and then the transmission spectrum are being manipulated with the electrode potential from 0 to 2 volt. And then the graph, and then I did the graph of the current versus voltage and vary the temperature from 0 to 2000 Kelvin. And then I look at what is the effect of temperature to the conductance. So then we need to understand second thing is the current equation. The current that the simulation got, the current is calculated from the transmission coefficient. So this transmission coefficient is got from transmission spectrum. So next is my Gantt chart. Okay. Now this is my result for the bulk single wall. So the left part is the single wall carbon nanotube and the right part is multi-wall carbon nanotube. So the difference is the transmission of single wall carbon nanotube at Fermi level is 2. However, at multi-wall carbon nanotube, it is 3 times higher. So the Fermi level, the transmission at Fermi level. So then I designed the device structure of single wall. So single wall is on the left, multi-wall is on the right. So this part is the electrode potential and this is the potential. So the difference between this structure is the gap distance at multi-wall carbon nanotube. So from here and from here, there is a gap distance. So I wanted to understand what is the effect of this gap distance to the electrical performance. So next, I simulate the transmission spectrum again. So the difference now is that multi-wall carbon nanotube had decreased the transmission spectrum from just now it was 6, but now it's 0.2. But this is the same for single wall bulk and single wall device structure. So then I simulate the current versus bias voltage. What we can see here, single wall is directly proportional to the bias, but the electric current does not increase distinctly. So if we zoom, we can see the difference in the temperature. And this is different for multi-wall carbon nanotube, where the voltage is not directly proportional to the current, as an armchair multi-wall carbon nanotube should be, because this armchair should portray a metallic property. And not only that, the value of current is actually smaller than the value of current flow in single wall carbon nanotube. So after that, yes, I look at the conductivity of conductivity versus temperature. So what we can see before, the temperature affect very small to the value of current. Uh, Although it had been varied until 2000 Kelvin for IV characteristic. So from this, we can see that a significant difference can only be seen from 0 to about 50,000 Kelvin, which is very high. So now what I did is I manipulate from 0.3 nanometer to 0.6 nanometer tunneling distance. And what I got is that the electrostatic difference potential here show that there is effect of gate around the metal and dielectric region. And then the potential is growing bigger at the junction. So this transmission, after that, the transmission spectrum at Fermi level is 0, and there are at the zero bias condition. So from here, we can see that the current versus bias voltage. So as the transmission coefficient decrease, the value of current also decrease. However, the current still conduct electricity as the voltage bias increase. But there is a constant or a stagnant value from 0.5 to 1.25. So the reason we can see, we can look, we can be described further by looking at the transmission spectrum. So if we look at the transmission spectrum here, there's a bias voltage of 0.5 until 1.25. The transmission energy for 0.5 until 1.25 is the same amount, and it differs at 1.5 volt, where the transmission energy had increased. So that is why the value for the current also increased during this time, and then this value is constant from 0.5 to 1.25 volt. So based on that, we can see that the transmission spectrum of multi-wall carbon nanotube for bulk simulation is actually 3 times higher than single wall. But the transmission spectrum for multi-wall carbon nanotube with gap distance is smaller than single wall. And the IV characteristic for gap distance of 0.3 nanometer is not directly proportional anymore and has a lower current value compared to the single wall. And this is also the same to the 0.6 nanometer, which has even lower current and stagnant value at certain bias voltage. And from the temperature conductance, we can see that there are no distinct effect at all. And based on that, we can say that supposedly multi-wall carbon nanotube should be able to conduct electric by 67% better than current of single wall carbon nanotube. However, we can see that the increase the tunneling distance, we have reduced the electrical performance. So that is all. This is my references, and that is all. Thank you.
Alright, thank you Fadlin. Thank you so much. Fadlin, just want to know you pakai software apa to simulate this one Is it
Quantum wise.
quantum wise So you're doing
Wise.
for the tunneling and also the probability of tadi apa panggil apa the probability of the current transmission probability
Yes.
I think this is something really good because I never see student done it before. Alright, so I open for Q&A right now. So I think we'll start with Dr. Suhana. Okay, Dr. Suhana, you have any question for Fadlin?
Just a short question, Fadlin.
Okay.
Why do you have to check the temperature? What is the concern?
Oh, that one was just to see if there is an effect to the conductivity or to the tunneling distance.
To
It was to further understand what is happening, if the temperature actually has an effect or not.
but dia tak ada effect lah kan?
No, because there
Actually,
are some materials,
changes. There is some changes tadi kan?
just very small changes.
Very small, tapi you can actually quantify it. maybe plus minus berapa changes with temperature variation tu.
Oh, okay.
Memanglah when you zoom nampak dia punya variation tu. So maybe you can just check what is the difference in the current percentage lah, maybe about 0.5%.
Oh, okay. I think I can do that.
Okay, that's all.
Alright. Okay, thank you.
All right. Okay, how about Dr. Mastura? Do you have any question for Fadlin? Dr. Mastura, can you hear us? Okay.
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 All right. In your result presented just now, as you increase the voltage, there is no changes observed in the transmission spectrum, right? But for voltage 1.5, it suddenly slightly increased. Is there any reason about that? Maybe can you elaborate a bit?
For this one,
No, I think before this, yang ada banyak-banyak gambar tadi.
is it this one?
Bukan. Lepas ni lagi kot. Next. Sini. Just now you said that for all biasing voltage from 0.5 up to 1.25, there's no different in term of energy. But for 1.5,
Oh, yes.
it changed. Is there any reason about that?
Yes, there is. Because the current, based on the calculation, based on the equation, the current that we got is from the transmission coefficient. So from here, we can see that at 0.5, the Fermi level from right electrode to left electrode, the transmission of energy only have this amount. So this amount is the same for bias voltage 0.5, 0.75, 1 volt, and also 1.25 volt. So all of this transmission value is the same. That's why the current is the same. However, when it reached 1.5 volt, the transmission had increased. So this value, where the Fermi level of right electrode to left electrode, so there is a value of transmission here. So that's why the reason, that is the reason why the current also increased.
Okay. That's all for me.
Oh, okay. All right. Thank you, Fadlin, for your presentation. So I'll give some time for the panel to give marks for you. So in the meantime, we move on to Jiawi. So Fadlin, you can switch off lah, your webcam ready, and then can boleh relax lah. Dr. Izala say very good because I'm chatting with her just now. I say, wow, how are you? I say very good. Oh, bagus Alright. So
Okay, thank you.
we proceed with Jiawi. Jiawi, can you take over the control? See whether you can share the content or not. I can see your face already. Oh,
Content, okay.
content okay. Okay, we wait first. We wait 1 minute first. You can maximize it. Maximize it. Let's see. Is it okay or not? Oh, okay. Can see now. Oh, I got some effect one. Can like. Okay, we wait first. Your one is by Dr. Amijan. Let's see rubrics here. So, how many slides you have? Let's see. 88.
28.
Oh, 28. All right. Okay. Dr. Mastura and Dr. Suwana, okay now? Boleh start?
Okay, I'm ready.
Okay. All right. Jawi, you can start now.
So, good afternoon to my panels, Dr. Michael, Dr. Masura, and Dr. Suhana. I'm Eng Jia Hui, and my FYP supervisor is Dr. Amin Jan. Today, I would like to present about my final year project, which is Experimental and Computational Analysis of Melting Process of a Phase Change Material, PCM, for Photodiode application. So, this presentation will beginning with the introduction, followed by problem statement, objective, scope of work, research flowchart, Gantt chart, literature review, methodology, results, data analysis, future work, and some reference. So now let me introduce about my project. Over the year, energy consumption has been increasing fast. Solar energy is one of the important sources of renewable energy. As we know, PV panel can change the solar energy into electricity. However, the efficiency of PV panel will decrease during a hot temperature. PCM, phase change material, can be used to cool down the PV panel during a hot temperature and improve its efficiency. The problem statement of my research is the efficiency of the PV panel will be reduced by the increment of surrounding temperature, and the solution is the melting process of PCM will be conducted in this research to analyze its ability to improve the efficiency of PV panel. There are three objectives in my research. The first one is to analyze the change of temperature and liquefaction of PCM in an experiment. Second, to simulate the geometry model of the PCM domain by using assistant software. Third, to compare the differences between the change of temperature and liquefaction of PCM for every 30 seconds in experiment and simulation. In this research, I carry out an experiment to analyze the melting process of PCM. Then, I designed the geometry model of the PCM domain by using assistant software. Next, I simulate the controls of temperature and liquefaction of PCM by using assistant software. Next, I compare the temperature of PCM versus time graph and liquefaction of PCM versus time graph, plotted from the experiment and simulation. And last, I will analyze and conclude the findings. So this figure shows my research flowchart. At the beginning, I study some related topics from journals and articles. Next, I carry out an experiment to investigate the melting process of PCM. And then I run the simulation part of the melting process of PCM. After checking there is no any errors, I compare and analyze the results. This figure shows the Gantt chart for my FYP1. Basically, for FYP1, after deciding the topics, I study some journals and understand and articles about my project, and then I carry out an experiment to investigate the melting process of PCM. And this is the Gantt chart for my FYP2. For FYP2, I run the simulation part, which is I install the ANSYS software and set up and run the simulation, and last I troubleshoot the problems. So after make sure there is no any problem, I observe and analyze the data. These are some literature reviews related to my research. The first one is the effect of graphene oxide nanoparticles on thermal properties of paraffin wax. The difference between this journal and my research is this journal add the graphene oxide nanoparticles into the paraffin wax. However, in my research, I only use the pure paraffin wax. Second, experimental investigation on using a novel phase change material in microstructure photodiode cooling system. In this research, the PCM experiment was conducted by using a PV panel. And third, simulation of melting process of a phase change material using assistant. In this research, paraffin wax RT55 was used as a PCM. However, in my research, paraffin wax RT35 was used. The last one is a thermal and state characteristic of a latent heat thermal energy storage unit. This journal discussed influence of two HTF passage configuration and single pass configuration on the melting process of PCM. Now I'm going to explain about the methodology of my research. First is the experiment setup. A specimen with 5 grams of paraffin wax RT35 was prepared and heated at 333 Kelvin, which is equal to 60 degrees Celsius for 900 seconds. The temperature and the liquefaction of the specimen was observed by using infrared camera. The temperature and the liquefaction of the specimen are recorded every 50 seconds. This figure shows the experiment setup. So from this figure, we can see that the PCM specimen was heated by using a digital ceramic hot plate at 60 degrees Celsius. Then the infrared camera was used to observe the melting process of PCM. The infrared camera was connected to image-tree analysis software. And then 9 points were pinned randomly on the PCM to get its average temperature. And then the color range was observed to get the liquid fraction when the PCM was melted. For the simulation part, ANSYS Front version R1 2020 software was used for modeling and simulation of the melting of PCM. A geometry model of the PCM domain was designed in 2D planar rectangular shape, as shown in this figure, with the length of 0.025 meter and the height of 0.02 meter. The calculations are performed using default commercial CFD code in ANSYS Front. The PCM domain was heated with a temperature of T equals to 333 Kelvin. So this graph shows the temperature versus flow time graph in experiment. And this graph shows a liquid fraction versus flow time graph in experiment. This is the simulated temperature versus flow time graph by using ANSYS. And this is the simulated fraction versus flow time graph by using ANSYS Front. This is the controls of temperature simulated by using ANSYS Front software. From this video, we can see that the blue color zone shows the low temperature zone, and the red color zone shows the high temperature zone. So, the red color zone was increasing, means that the PCM was heated until all the zone become high temperature, which is the red color zone. And this is the controls of liquid fraction simulated by using ANSYS Front. The blue color zone shows the PCM is completely liquid, completely solid, and the red color zone shows the PCM is completely liquid. So at the end of the simulation, all the PCM has been turned into liquid phase. This graph shows the comparison between the change of temperature of PCM for every 30 seconds in experiment and simulation. The red line shows the simulation results, and the blue line shows the experimental results. From this graph, we can see that the melting point of PCM of paraffin wax RT35 is around 308 Kelvin, which is equal to 35 degrees Celsius. The maximum temperature reached is 321 Kelvin, which is equal to 48 degrees Celsius. This graph shows the comparison between the change of liquid fraction of PCM for every 30 seconds in experiment and simulation. We can see that around 500 seconds, all the PCM have changed into this liquid state. So there are some differences between the experimental and simulation results. The simulation results and experimental results shows discrepancy due to some reasons. For example, environmental disturbance. Because the experiment was carried out in an air-conditioned room, so the temperature applied to the PCM will less than 333 Kelvin. This will influence the experiment result. Next, contact thermal resistance between the specimen and the seed. And third, chemical impurities in the paraffin wax R35. Sorry, doctor. So, however, although the values have some difference, but both graphs show great agreement. This is the future work of my research. The PCM can be implemented into to PV panel to optimize its efficiency during high and low temperature. Next, the PCM has low thermal conductivity, and it can be enhanced by adding the nanoparticles into the PCM. For example, graphene-based nanoparticle PCM. So these are some references related to my research. That is all from me. Thank you.
All right, thank you, Jerry. Jerry, want to know how do you complete your work? Because it's lab work, right? How do you do that in MCO?
I do it in first sem 1.
You do it for SEM 1 lah.
And the simulation part, I do it in sem 2.
Oh, so the hardware already done lah before that.
Yes.
And then the question on your PCM, right? It is actually a solid, then he turn into liquid, right?
Yes.
Then after that become liquid already, then cannot become solid back.
Can. If you cool down, it will become a
Oh.
solid.
So how many times can use like that until the efficiency no more already? Like how many times can transition from solid liquid? Like is it 50 times?
From the graph, I melt it in 900 seconds, but actually from 600 seconds, it will turn into the liquid.
Oh, so in for solar panel, if you use it, can do many times one lah, can transition many times one lah.
Yes.
Oh, okay, all
The
right.
temperature of surrounding is cooled down, so the PCM will change into solid again.
Okay, all right. So I open Q&A to Dr. Suhana. Dr. Suhana, you have any question for Jiawi?
Hi, Joey.
Hi.
I just have one question about the PCM, right? You're going to put it on the solar panel. It will be coated on the solar panel, is it?
Yes.
So if you put on the solar panel, there be any changes in the temperature or not?
It will, because the surface of the solar panel will become overheat in a very hot temperature. So the PCM, the function is to help the surface of PCM to absorb the heat on the surface of PCM, surface of PV panel. So this can maintain the efficiency of the PV panel.
If let's say you have PCM on the silicon oxide, will this graph change?
Sorry, can you repeat?
If you have PCM material on the silicon oxide, basically the solar panel is made of silicon oxide, right?
Yes.
Polysilicon. If you have the PCM on the polysilicon, will this graph change?
Will this graph change?
Ah,
Um, no, this graph will not be changed because this graph is observed on the characteristic of the PCM, and the graph on the surface of solar panel will be different. You get what I mean?
yeah. Okay, I understand.
Ah,
Thank you.
thank
All
you.
right, thank you. How about Dr. Mastura? You have any question for Jiawi?
Yeah, I have.
Okay.
Okay. Correct me if I misunderstood about your project. Basically, you are change the state of PCM solution from solid to liquid by heating it up. From what range of temperature? May I know it?
Sorry, can you repeat?
Range of temperature that you've been tested for the experiment.
From 300 Kelvin, which is equal to 27 degrees Celsius, to 321 Kelvin, which is equal to 48 degrees Celsius.
Why you stop at that temperature?
Because from you can see the graph from that graph you can see that the temperature has become constant around 321 degrees Celsius. So
Mm.
321 Kelvin. So I stop it at there. And this graph already shows the PCM already melt into the liquid.
All right. So do you think that the amount or the volume of the liquid used to coat the PV will affect of the temperature range rate, the rate of temperature range?
Sorry, I can't understand your question.
Okay. Because you're going to coat this PCM on your PV, right? So
Yes.
do you think that the amount or the volume of a PCM coated on the PV surface will affect the rate of temperature changes?
Yes, it will affect.
So how much the amount of PCM that you use in your experiment? And
Just 5 ml only, which is in a small size specimen.
Okay, so if we increase the volume, so what will happen? Is it the rate of changes will increase or decrease?
The rate of if I increase the volume, the rate of changes uh I
How about the temperature pattern? Is it will become faster or something delay about the graph that you show right now? If we imagine that if we increase the volume of the PCM used, what will you expect will happen to this graph?
mm, if I increase the volume, so this graph, I think this graph, uh, I think because this in this I use a small amount of PCM only in this experiment. So I do it in a large amount. Maybe the time to reach the maximum temperature will be increased because it needs some time to melt all the PCM.
Mm-hmm.
The time will be increased. The rate will be changed.
So in terms of your problem statement, it stated that to increase the efficiency of the PV means that you need to increase the temperature. Can we look at your problem statement again? Efficiency of PV panel will be reduced by the increment of surrounding temperature. Oh, so means that to make it efficient, uh, efficiency will reduce. So you need to reduce the surrounding temperature. So in that case,
Reduce the temperature on the surface of the PV panel.
I'm sorry, repeat again your answer.
I need to reduce the temperature on the surface of PV panel because the surrounding temperature I cannot change it, right? So I apply the PCM on the PV panel, try to cool down the surface of the PV panel. You get what I mean?
Okay, so the temperature that you measured in your experiment is the temperature of PCM or the temperature of
The temperature of PCM.
PCM?
Yes. This is not the temperature on surface of PV panel.
Oh, okay. All right. Okay. Okay, that's all.
All right. Thank you,
Mm.
Dr. Mastura. All right, Jiawi, thank you so much. Jiawi, Dr. Amijan have a new baby at home, ah? Is it?
I'm not sure.
You're
He
not
didn't
sure, ah? Oh, because my student, the other WebEx one, cannot see him online, so we don't know where is he.
I know.
Oh, you know
Okay.
lah.
Yeah.
Okay, all right. Thank you, ah. All right,
You.
so we move on to the next one. Chanam. Chanam, can you take over and show your face and then share your content? Uh,
Hello, doctor.
wow, we're so smart, ah. Oh, yo. Oh, okay. Can see you.
Uh,
Lagging a bit already. Can see you already. Can you share? You know how to share slide or not?
I'm finding. I'm
Find
searching.
there is a
Share,
share content.
share screen. Is it okay?
Try and see. Share screen, share content. Something is opening already. Wait, it is loading right now. Can see already. Yes, Dr. Zahara optimization 22 strain. Okay, so we give some time for the panel to give marks for Chiawi first. All right. So you maximize first?
Already.
Maximize already.
Uh-huh.
Okay. Oh, it's a bit slow. I think your internet you're not using Unify mobile.
Mobile, because my hometown, the internet is a bit not good.
Oh, okay. Okay, we see how first like if it's lagging a lot later on, then you can switch off your video lah. If it's not lagging, then we can see your face lah. Huh? Okay, I'll give some time
Okay.
for the panel first to give marks first.
Okay.
10 minutes. How many slides do you have? Let me open here. We can see your slide.
35.
Oh, 35. 35 okay lah. Alright. So Dr. Suhana and Dr. Mastura, I can start now, okay?
Okay.
Alright, thank you. Alright, Chenam, you can take over now.
Okay. Good afternoon, doctors. My name is Goh Chen Nam. So my FIP title is Optimization of 22 nanometer strain silicon nanowire FinFET transistor for higher on current. So this is my presentation outline. So according to Moore's law, the number of transistors in a microchip will double every 18 months. The size of transistor becomes smaller to fit into a microchip. So a few issues will occur when downscaling the conventional MOSFET, such as the threshold voltage, short channel effects, and others. So we can use the alternative solution to solve the issues such as the new materials, new structure, and mixture of materials and structures. This is the comparison between the conventional MOSFET versus FinFET. So overall, we can see that the SOI FinFET has the better performance compared to the MOSFET, especially the current ratio. So what is the Takuchi method? Takuchi method is an optimization method to minimize the number of experiments and reducing the cost and time. So in this project, I'll be using the level 9 Takuchi method. So this is the literature review for ways to reduce the short channel effects, literature review for strain silicon, and literature review for multi-gate transistor, and finally the literature review for Takuchi method. Overall, we can see that the literature review that I have reviewed shows the on current has been successfully to be maximized. So for a problem statement, in this project, I will be only focusing in solving the problem of the low driving current. In this work, I will be creating a nanowire FinFET transistor with 22 nanometer gate length. Then I will add strain silicon to the transistor. Next, I will optimize the parameter using the Takuchi method, and finally observe the performance. My research objective: first, I will be build a structure of strain silicon nanowire FinFET transistor, and second, I will be optimize the process parameter of strain silicon nanowire FinFET by using the level 9 Takuchi method. For my research scope, the strain silicon nanowire FinFET is created by using the Centaurus TCAD tool and focus on the 22 nanometer gate length. Second, I will optimize the performance parameter using the Takuchi method with the Minitab software. And the performance output I will be focusing on is the on current, and the control factors to focus on is the thickness of site, fin width, and channel length. And third, the overall device performance will also be obtained, such as the threshold voltage, subthreshold loop, on current, and off current. For my methodology, this is my general flow chart. First, I will do about the literature review. Second, I will develop a FinFET using the TCAD tools and simulate the device. If the validation is successful, then I will add the strain silicon to the device. Then I will optimize the device using the Takuchi method, run the analysis and benchmarking, and finally, result discussions and report writing. This is my Centaurus simulation flow charts, and the software required for this flow is the Centaurus TCAD tool. So in the Centaurus workbench, I will add the Centaurus structure editor tools to create the FinFET structure. Next, I will test it. If successful, then I will add the Centaurus structure editor. I will add the strain silicon to the Centaurus structure editor and also add the stress-related model to the Centaurus device. Next, I will run simulate it. Then I will get an IV characteristic simulated from the Centaurus device. Then the IV curve can be plotted using the inspect tool for analysis. This is the statistical simulation flow charts. For this flow, the software required is the Minitab software. So after getting the result from the Centaurus, I will move the result to the Minitab software. So here I will run two analysis, which is the Takuchi method, and next is the ANOVA
analysis of variance. So over here from the Takuchi method, I can get the best combination of parameters, and from the ANOVA, I can get the greatest effect parameters. So for result discussions, this is the FinFET structure that I have created from the Statistical tool. So this is the stress distribution diagram, and we must note that the silicon dioxide is hidden over here so that we can observe the channel stress distributions. This is the parameter that I have used in simulated the device. So I have used the 22 nanometer channel length, and also the control factors are channel doping, film width, and thickness oxide. This is the validation that I have run. So this is the comparison between the research paper and simulation for 1 volt gate voltage, and this is the comparison between the research paper and simulation for 0.05 volt gate voltage. So overall, we can see that do not have much difference between the research paper and the simulation. Table 7.2 shows the levels of control factors, and table 7.3 shows the overall Takuchi method result. So the control factors of Takuchi methods are thickness oxide, film width, and channel doping. So for the red boxes, in the red boxes, is the experiment number 3 has the highest signal to noise ratio value. And figure 7.4 shows the SFI log of Takuchi method, and figure 7.4 shows the response figure for SFR ratio. Since the on current is needed to be as large as possible, the formula for the SNR of Takuchi methods is using the larger the better. Hence, the level of parameters with larger SNR is the level to achieve the higher on current value. Next, I will talk about the statistical analysis for ANOVA. Table 7.5 shows the result for analysis of variance. So over here, the thickness of size has the greatest effect to the on current, and channel doping has the least effect to the on current. So now I will talk about the validation of the result. Figure 7.5a and 7.5b shows the result of 27 combinations experiment. So from the 27 experiment number 9 has the highest on current value. Hence, the combination of experiment number 9 is matched with the result of paper 7.3. So this is the current voltage characteristic according to the experiment from table 7.3. So for the blue color line is the experiment number 3 has the highest on current value, which is matched with the table 7.3. So figure 7.7a shows the IV curve with channel doping as varying parameter, and the thickness oxide and film width is constant. So figure 7.7b shows the IV curve with film width as varying parameter, and channel doping and thickness of size is constant. And now this is the figure 7.7c shows the IV curve with thickness of size as varying parameter, and channel doping and film width is constant. Figures 7.7a to 7.7c prove that the delta and rank in the table 7.3 is correct. So for conclusions, strained silicon nanowire FinFET is built using the Statistical tool. The device performance is optimized based on 3 device parameters using Evernight Takuchi method. The best combination of parameter to on current is obtained, and 4th, the rank of greatest effect parameters to on current is obtained. For future work recommendation, use higher order of Takuchi methods such as level 11, level 13, or level 27 to include more control factors. Second, reduce the dimension of transistor using gate length less than 22 nanometer. And third, we can try the other electrical properties such as leakage current and threshold voltage. So this is my Gantt chart for FYP1 and Gantt chart for FYP2. This is my reference, and thank you for listening to my presentations.
Thank you, Chenam. Chenam, just want to ask, the level, right, is selected in CentOS itself, the level 9 or 13?
No, the level is decided by ourselves. So over here from the table 7.2, the level actually means like 0.4 for thickness of site. We assign one level for the each control factors.
Oh, so you came up with this one lah. It's not auto-generated from the CentOS lah.
It's auto-generated by the Minitab software, which is the Takuchi method.
Oh,
Takuchi method has its own arrangement.
so you mini tab, then you copy paste into CentOS lah.
Yes.
Oh, okay. And then during the MCO, how do you have access to this software?
The Minitab software I get is from online, which is the trial versions, and the CentOS software is I have to wait my supervisor to make
Oh.
that software online.
Yeah lah, because Dr. Izala set up only, then you got access lah. Because the lab student are also using it, right? Okay. Just want to ask another question is that, are you gonna publish this or not? I mean, not for the UTM one lah. You gonna publish or not? A lot of good result there, I see. Oh, huh? Dr. Zahra got say gonna publish outside or not?
I will see. I will see again.
You see again, All right.
Uh,
Okay, so I open for Q&A. Dr. Suhana, you have a question?
Chinam, how do you introduce the string?
how am I introduce the string? So actually in CentOS, right, we have the tools like the CentOS structure editor and CentOS process. Last time I'm using the CentOS process, but the simulation time is too long. Like it would take like the whole day to run one experiment. So after that, I changed it to the CentOS structure editor. The method that I introduce the strain silicon is induce the strain inside it, which means it's the alternative solution for me to introduce the strain stress into the transistor. Do you understand?
Is it induce the string in the structure editor?
Yes.
So you put some value of the string percentage like that.
I give the over here.
Huh?
Can you see the stress applied on channel? Which means I directly give the stress to the channel. I did not put the strain silicon on it.
Okay, I understand. So this stress is not part of the parameter that you vary, is it?
No.
Okay,
This is fixed constant.
Okay, understand. Thank you.
All right. Okay, Dr. Mastura.
Okay, so in your optimization, can you go to your problem statement slide?
Okay.
Okay, it seems that there are four main problems that short channel effect, low driving current, high substrational slope, and high leakage current. So it seems that you chose to optimize in terms of driving current, right? So
Yes.
is there any reason that you chose that issue rather than the other three?
For these questions, because I have reviewed back to the literature and I found that not many people is doing on optimize the low driving current. Most of the people is choosing like the high leakage current. They are trying to optimize that problem. Then no people try to solve the low driving currents there. So I would like to try on this.
Okay, so in terms of application, that criteria in terms of ranking of priority, so that So is it related to the priority in terms of design, so that you look on that issue?
Sorry, can you repeat?
I mean, the problems, there are four main problems that you list right now, and you focus on low driving current. So your justification of focusing on this issue, because not many people doing in this area, right? In terms of
Yes.
application, is it too critical? Is it very critical to in terms of this driving current issue, so that maybe that's the reason why not many people looking on that? Or
Because the low driving current problem, right? In the IC, if we left out this issue, then the stability of the IC will become unstable. So we need the high driving current in to maintain the stability of the IC. So it is also critical in continue develop the IC path.
all right. And then by performing this optimization using Taguchi methods, there are three main parameters, like what just now, thickness of gate oxide, what else? Film width, and what is the last one? There are three parameters, right?
Channel doping.
So how did you decide these three, or based on optimization you come up that these three parameter?
Because I reviewed back to the literature, right? So many people like they use the special characteristic of the fin fat, because like the fin width, the fin height, something like this. There's the special characteristic that only exists in the fin fat. So I review back. Many people do the optimization by using the fin width, fin height, and the top fin width or fin height. They are varying the same, like the dimension of the transistor. So that's why now I choose the dimension of the device, the fin width. Then I choose the doping, like the channel doping, and also use the dielectric material, which is the thickness oxide. I want to see the difference is between these three control factors.
Okay, understood. Thank you.
All right. Thank you, Dr. Mastura. Okay, Chiana More, thank you so much for your presentation. All right, we will start the next participant to set up Ainun. All right, Ainun, can you?
Thank you.
Okay,
Thank you,
okay,
Doctor.
Chiana.
Okay.
Ainun, can you enable your webcam?
I'm fine.
You can disable your one already, Janam. Ainun, can see you. Can nampak kipas juga.
Hold on, Doctor. I'm finding how can I save.
You there down there on the in the center bottom there, got start my video and the video one. Just press on it only. Tak boleh. Let me see.
Cannot find.
There down there on the bottom there got the mute my microphone and then also.
Over here, right?
No. How come you don't have one? Your WebEx, where is your WebEx?
Stop sharing.
Okay, can already. Then you just close your. Okay.
Okay.
We get back to Ainun. All right. Ainun, can you share your. Can you share your content?
Okay, Doctor.
Okay. Apa kita buat slowly.
Can you see my slide?
Dia tengah loading. Nampak.
Loading.
Okay. Boleh nampak. Boleh maximize. Boleh maximize. Okay, dah nampak. Okay, kita tunggu sekejap. Kita panggil panel. Tulis dulu. This one. Okay, ni supervisor Dr. Zahra jugalah ha. Okay. Tunggu sekejap ya. Okay, Dr. Suhana, Dr. Mastura, can start now?
Okay, sudah.
Alright, boleh.
Boleh.
Okay, I know.
Alright.
You may start now.
Okay, Assalamualaikum and a very good afternoon to all panels. So my name is Ainun Khairia binti Taib under supervision of Dr. Zahra binti Johari. So the title for my final year project is Simulation Study on Fully Depleted Silicon on Insulator, FTSOI, MOSFET Channel Variation, Dimension Variation using TCAT. Alright, so okay, this is the presentation outline for overall slide. Okay, for research background. So transistor is the heart of many electronic devices and it can be found on your smartphone, laptop, television, and also camera and so many more. Alright, so this is the evolution trends of MOSFET that's starting from 2005. So now we are in 2020. So it is expected that MOSFET transistor channel is below than 5 nanometer. So as you can see, starting from 2013 onwards, many researchers are working so hard in looking alternative that can to sustain the transistor performances. So some of the example, they are using new advanced material, new device architecture. So what is the purpose of using this material? Because we want to put more transistor into a single chip. So next, so as stated by Moore's law, the number of transistor on silicon chip will roughly double every 18 months. So now all of the transistor and other part of the device are reached into nanoscale dimension, and further reducing the size would lead to the first one, short channel effect, second, power issue like high static power caused by the intrinsic leakage currents. So why scaling down transistor is important? Because we want to improve the performances in terms of smaller chip size, faster speed, lower power dissipation, low leakage current. However, even we manage to improve all of this performance, we are still facing the issue of the channel effect. Okay, so this is the literature review that related to the fully depleted SOI, while this is the literature review that related to in designing FTSOI. So therefore, this work improved previous work done that focused the channel dimension effect on electrical properties. Right, so this slide is about problem statement. So the problem is scaling down transistor dimension has led to the short channel effect and performance degradation. So previous work has been done on new advanced material and new device architecture. So in this work, I varied the gate length of the FTSOI MOSFET, studied the performance of the FTSOI MOSFET, and lastly, I will study the electrical properties of the FTSOI MOSFET in terms of threshold voltage, off current, on current, and sub-threshold slope, which is SS. So this is the research objective, which number one, to develop fully depleted silicon on insulator MOSFET using TCAD. Second, to study the electrical properties of fully depleted silicon on insulator MOSFET by varying the channel. Okay, for research scope, the software that I am using to simulate all the result is I'm using Synopsys Centaurus TCAD. And the device, I focus on the fully depleted silicon on insulator MOSFET. So here I generate the IV characteristic in terms of the threshold voltage, off current, on current, and the SS. And then I vary the gate length that focus on the short channel that less than 50 nanometers. So here I'm choosing 5, which is 40 nanometer, 30 nanometer, 25 nanometer, 15, and 10 nanometer. Right. So this is the methodology where I start with literature review, then develop the structure, vary the gate length, vary the gate oxide thickness, generate the IV characteristic and check the electrical properties, and lastly study the performance. So this is the structure devices of FD-SOI, where there is a silicon SOI film thickness in between of the drain and source. Then we have additional layer of uric oxide, which is called BOX. So in this work, there are two things that I vary. First one is the gate length. As you can see, there is a structure when LG is 10 nanometer and the other one is 40 nanometer. Then I vary the gate oxide thickness. First one is 5 nanometer and second 8 nanometer. So on my right, there is the VG and VD fixed, which is I take 1.5 volt and VD 0.05 volt, sorry. So here is the Gantt chart for FYP1 and the blue one is the Gantt chart for FYP2. So result and discussion. This is the IDVG characteristic of 10 nanometer and oxide thickness of 5 nanometer. So in here, for VG 1.5, I obtained the VTH of 0.54 volt, ion 0.63 milliampere, I of 864.19 femtoampere, and lastly SS 106.28 millivolt per decade. So how I obtain the result, this is how I extract. As you can see, I on, VTH, the SS, and the I off when the VG is 0. Okay. So this is the gate length versus VTH, which as the gate length is reduced, the VTH is decreases too. So as you can see, the thicker the thickness of the gate oxide, the lower the VTH. So in here, the thicker is the 8 nanometer. And at 40 nanometer, there is no much effect on the oxide thickness to the VTH. And as gate length get lower at 50 nanometer, there is a huge effect between the oxide thickness. However, the data of the 8 nanometer of the oxide thickness is not stable compared to 5 nanometer. It is maybe probably because of the additional effect that I am not taking account into this project, which is maybe quantum effect. And therefore, the lower the VTH, the shorter the time needed for the electron to flow between the source and drain terminals. So next, this is the result of gate length versus off current. So from the result, as you can see, I off is increases in unit of femtoampere, okay, as the gate length is decreased. So at the gate length 10 nanometer, there is high significant effect that is below 10 nanometer. Then started from 15 nanometer and above, there is no much effect between the 5 nanometer and 8 nanometer. So here is the gate length versus ion. So here, the shorter the gate length, the higher the ion. At 13 nanometer of gate length, the ion is obtained at the same value for both the oxide, which is 0.34 milliampere. And from the result, it shows that ion is more higher than I off because here we obtain milliampere while I off is in femtoampere. So in obtaining low leakage current, the ratio of the ion over I off must be high. So this is the result for gate length versus the threshold slope. So as you can see, the lower the SS, the better the performances. As gate length is reduced, the SS is also decreasing. So the lowest of SS is achieved at 10 nanometer with the oxide 8 nanometer. So as conclusion, for the first objective to develop fully depleted silicon on insulator MOSFET using TCAD. So the gate length are successfully varied. And second, to study the electrical properties of fully depleted silicon on insulator MOSFET by varying the channel dimension. So here the performance of FD-SOI is observed at LG 10 nanometer with electrical properties of VTH 0.54 volt, ion 0.63 milliampere, I of 864.19 femtoampere, and lastly, SS, I obtained 106.28 millivolt per decade. So this is the future work. Maybe we can investigate in terms of channel concentration in the future. And second one, to optimize using Taguchi method and test its feasibility in device application like CMOS. This is the last slide reference. So that's all from me. Thank you.
Thank you, Ainun. Okay, Ainun kan,
Yeah.
for your structure tu, what is the width ah?
Structure tu.
You do with length, right? So the width tu you pakai apa width ah? Ada tak your simulation dia ada specify what width do you use or not? Berapa width dia?
Oh, you mean the get length?
Bukan,
Right.
gate length you dah bagi. The gate width ada tak? I mean in your simulation, your gate width you set as berapa lah? Sebab you ada LG kan? LG ada.
Oh,
WG tahu tak?
uh,
WG.
that one I
Hmm.
did not take it because I'm working on 2D
Oh, tu
dimensional. So, yeah. So
So
I
dia
obtained in 2D.
open in 2D tapi yang di ada satu dia tak specify lah berapa atau
Yeah.
maybe software ni dia
Uh-huh.
dia bagi WG set ni tak adalah sebab
Uh,
sengaja.
and I think for all the structure using the same width.
Yes. So
Ah.
in case kalau you can find out is better lah you put in thesis sebab dia kata bagus lah semua okay just nak tahu W tu dia set berapa lah in the
Okay.
simulation. Okay. That's my
Alright.
only question lah. So
Okay.
now we ask Dr. Suhana.
Yang width tu maybe betul lah Michael. Ainun can find out what is the default width in the Centaurus.
Okay.
Ada default dia. Saya tak pasti. Is it 10 nanometer ke 100 nanometer ke?
You can find out lah
Betul lah, you
Alright,
have to
doctor.
specify kat info.
Alright.
Then why you when you vary the gate length, you vary from 10 nanometer to 15 nanometer, is it?
To 40, yeah. I'm choosing below than 50 nanometer.
Kenapa tak pergi bawah lagi? 5 ke 2 ke?
Because according to the timeline, I know that in 2020 we are now reaching below than 5 nanometer, but I think it is worth for me to investigate and choose 5 variation of gate length, and the maximum that I can go is 10 nanometer for this project.
The previous part you ada discuss about subthreshold slope kan?
Yeah.
Tunjuk sekejap. Laju sangat you pergi. Nak kerja apa saya pun tak tahu.
Oh, I'm so sorry.
Yang before the conclusion.
This one.
Ni subthreshold slope. Okay. So yang subthreshold slope is ini memang graph subthreshold slope. So you vary the T-ox 5 nanometer and 8 nanometer.
Yes.
Okay, tapi subthreshold slope you kata yang atas ni lagi bagus.
Yeah, the lowest SS is achieved at 10 nanometer when TOX is 8 nanometer.
TOX 8 nanometer, tapi yang ni kat bawah ni tak okay ke? Yang this one is more than 100 but there is some yang below 50 kan?
Oh yeah.
So yang mana better? SS tinggi ke SS rendah?
The lower. So the TOX 5 nanometer. I'm so sorry for that.
TOX
5 nanometer.
5 nanometer. Oh, you dah letak sini dah. So conclusion pun kena tukar.
Okay. Thank you. Sorry for that.
Okay, thank you. Setuju.
Alright, Dr. Mastura. Dr. Mastura have any comment? Okay, Dr. Mastura is here.
Sorry, selalu macam ni. Okay, so you have tested for several combination of gate length and oxide thickness. Can you conclude out of this combination which one is giving the best parameter in terms of performance by combining all the subthreshold, V3 SS, V threshold, and the other two. Okay, which combination?
The best combination that I obtain in here is when the LG is of course 10 nanometer and TOX 5 nanometer.
5 nanometer.
Yeah.
Okay. Boleh tengok tajuk kamu tak?
Oh, boleh.
Sebab bila saya tengok table of saya punya jadual ni macam tajuk lain.
Hmm. So this is my final tajuk.
Okay, sebab dalam saya punya timetable ni phosphorine based logic gate. Okay, dah ni yang latest lah. Alright. Okay lah, tu je lah soalan saya.
Okay. Thank you Dr. Mastura. Alright, thank you Ainun. Dah habis
Thank
kan?
you.
Kita last one. Kita ada the last one nanti. Wei Jian. Wei Jian, are you here or not? I check with you just now. You tak reply pun Wei Jian.
Good afternoon, doctor.
Ah,
Can you listen clearly?
yes, can say. Oh, very smart. Smart. Okay. Can you share the slide?
Yeah, sure. You can listen clearly, right?
Can listen clearly.
Oh, all right, okay.
Okay. Share content.
Can you see my slide?
Can. But how come when you talk got a lot air one like a boo, like windy like that? Oh.
Oh, I switch off my fan first.
Switch off. Don't switch off lah your fan. Switch off your fan later you hot
Nanti berpeluh pula present.
Berpeluh.
Kesian dia.
Now, can listen better.
Can. Now very clear already. So we need for the panel to fill up the marks first. Alright. So
okay.
how you feeling? Okay, makan already?
Yeah. Dah makan.
So final exam coming soon?
Yes.
So this one graphene sensor, right? Do you have to go to the lab and do it? So how do you do it? This one experimental, right?
For the lab one, I have done on my last semester. So this semester, I only focus on the doing circuit and running the program on the Python.
Oh, so how do you do the circuit? You got time to finish?
Yes, I can finish only until the LDA part only lah, the Python.
Okay. Alright. So Dr. Suhana, Dr. Mastura, we can start now, right? Okay.
Yes.
Okay.
Yes.
Okay, thank you. Okay, Vijan, you can take over now. Alright.
Okay. Good afternoon to all the panels. I'm Wei Jian. So I will present my FYP, and my title is Paper-Based Graphene Sensor by using the electronic tongue application. Okay, this is my presentation outline. Okay, let me do some short introduction on this project. You know that if humans do not have the sense of taste, they are not able to distinguish the taste of the food. Therefore, the taste sensor is able to help them to distinguish the taste of the unknown food. Okay. The paper-based sensor is introduced in this project because the metal-based sensor mostly cannot be recyclable and non-disposable. Therefore, the advantage of using paper as the substrate of the sensor because of its disposable and low cost and lightweight. Okay, these are the journals paper that related with this project. And the main finding of all these journals paper is the authors are successfully to distinguish the taste of the sample by using the type of sensor, electronic tongue, like paper-based and also the metal-based electronic tongue. Okay, this is my project statement. The first statement is the PC-based electronic tongue like ST2ET is not portable and is very expensive. Therefore, my proposed solution is the Arduino is used for parameter extraction due to its cheap and also portable. The second is the previous work by Mr. Jiang focused on the resistive-based sensor only. Therefore, my proposed solution is to add one more, which is the capacitive-based sensor to increase the accuracy of the taste identification. Okay, this is my project objective. The first one is to utilize a sensor with combination of the resistive and capacitive operation. The second is to implement the Arduino-based identifier for response to the taste of the sample. This is my project methodology and is divided into four parts. Later, I will explain it detail later. Okay, this is the design of my paper-based sensor and is made up of filter paper and also the graphene cellulose ink. And your right-hand side is the schematic circuit of the sensor, paper-based sensor. Okay, now I will expand on the first stage, which is the sensor fabrication and characterization. Okay, the first step is to prepare the graphene and cellulose ink with the ratio 1:3. And I have done this on my last semester. And the next one is the electrode sticker pattern is cut and attach it on the screen printing kit. And the picture on the right-hand side is the screen printing kit and also the pattern as well. Okay, the third step is we use the pink color pink chemical photo emulsion is applied on the whole sticker and also the screen printing kit. And it place it in the dark room, left it for a day. Finally, the sticker and the electrode pattern is removed. And after that, the screen printing technique is carried out. Okay, now I will move on to the second stage, which is the implementation of Arduino-based identifier. So this is the schematic diagram of the Arduino-based identifier. As you can see, the green color box one inside consists of the paper-based sensor, which is connected with this circuit. So this is the experimental setup for the Arduino-based identifier, and it is connected with my PC and also the paper-based sensor. Okay, now I will move on to the third stage, which is parameter extraction and data collection. I use the salt solution as the sample of salty taste. So the resistance value and capacitance value, they are recorded into this table that I extracted from the Arduino serial monitor. And this process will repeated 10 times and by using a sensor which named as the sensor DEV1 for the salty taste. For the sweet taste, I use sugar solution as the sample, and the process is also same as the previous taste, but the sensor will be replaced to the new sensor, which is sensor DEV2. Now this one is for tasteless. I use plain water as a sample, and the process is also the same, but the sensor is replaced by the new sensor for the sensor DV3. Okay, after that, the features are extracted into this table. Now I'll explain through each of the feature. The feature one is the resistance as t equals to 1 means that the first value of the resistance value from the previous table that I have done. The t equals to 1 means is the first value. The t equals to 10 is the 10 value of the resistance value. The t equals to 4 is also the fourth value of the capacitance value. For the gradient of resistance and capacitance graph, later I will show you on the result and discussion part how to determine the gradient. Okay, this is a final step of my project, which is supervised learning with LDA. Now I will focus on the selection of features combination. The combination must be one resistive, one column of resistance, and also one of the capacitance value. It can be combination, it can be features 1 and 2, 1 and 4, and 1 and 6, and so on. This is for 2 features only. After that, I have to check the mean accuracy score for the 2 features, 4 features, and 6, all the features, just to check whether it is higher scores or not. If is higher scores, then the process will be stopped. If no, then the process will be repeated. Here's my Gantt chart of FYP1, and this one is for FYP2. Okay, now I will expand on my result and discussion. There are 7 sensors are successfully fabricated. I name it as DV1 to DV7. So this is the graph of the resistance against time of the source solution. As you can see, the gradient can be determined here on the slope of this line of the graph. Okay, this one is for sweet taste sugar solution, and this one is for tasteless plain water. Okay, for this one is the graph of the resistance against time of the source solution, salty taste, and this one is for sweet taste, and this one is for the tasteless. Okay, now I will expand on the result of my LDA plot. And the mean accuracy score is 0.7 if the 2 features are used. The feature used is the resistance as t equals to 10 and capacitance value at t equals to 4. This is the result for the 4 by using the 4 features, and the accuracy score is 0.8, which is higher compared to using 2 features only. And the features used is the t equals resistance at t equals to 1, t is equal to 10, and capacitance at t is equals to 1 and t equals to 4. Okay, this is the result for all features. You can see this is the highest amongst of the by using 2 features and 4 features. Okay, I found that there are some weaknesses on this project. The first weakness is the paper-based sensor cannot be reused after several trials of testing because the paper will become soft, and this will cause the capacitance value show INF instead of showing exact value, and this may reduce the accuracy of the LDA plot. For the second weakness is the sensor may not be detect the solution drop in a short time and causing the both values constant after several time of testing. And this is the second reason which will also cause the reduce the accuracy of the LDA plot. Okay, the responding times of each trial are different due to the solution may not drop at the exact location on the sensor. This can be solved by using the diffusible effect. Okay, the conclusion of this project is a paper-based graphene sensor having resistance and capacitance connection is successfully fabricated. Second is the filter paper is suitable for sensor fabrication, but only for single use. The third one is the more the feature extracted, which is the total 6 features, the taste classification will be more obvious. These are the reference that I found. Okay, I think that's all for my presentation. Now is a Q&A section.
All right, thank you, Wei Jian. Okay, so Wei Jian, I'll open this for Q&A right now. We'll start with Dr. Suhana.
Hi.
Hello.
Good afternoon, Dr. Sana.
Afternoon. I want to ask whether did you study the property of the you use graphene, right?
Sorry, I didn't hear it clearly.
You use filter paper, then after that, did you coat with graphene or it's just a filter paper?
The graphene ink on the filter paper.
Graphene ink. So the one that actually sensing it is the graphene ink lah.
Yes.
So did you study the property of how they actually sense this sugar solution and the salt solution?
I mainly focus on the LTA plot, but I do not study on the purpose that you say just now.
What tools did you use for machine learning?
Python.
Python. Oh, okay. You put it in the Python. Okay. It's an interesting project. That's all. Thank you.
All right, thank you.
Thank you, Dr. Suhana. Wow, Python is really good. Are you working in Intel later? Oh,
No. No.
all right, we're gonna go to Dr. Mastura right now.
Okay, so basically, if the user going to use your sensor, how actually the sample can be tested? I mean, how the result will be displayed in your in using your circuit? An indicator there?
You do you mean the how the resistance value is determined, right?
Yeah,
To-
yeah. Maybe is that your circuit able to give any indicator to the user? Let's say I put any sample, unknown sample to your sensor, and then tune it to your circuit, Arduino, right?
Uh,
Then,
Before I using the by testing the paper sensor, I only use the one of the capacitor test of the value first. After
mm-hmm.
that, I have to use the to measure the paper sensor for the resistance value, the capacitance value.
Oh, okay. So basically, the range of capacitance and resistance value will discriminate the type of taste lah, right?
Yes.
Okay. And one of your conclusion or recommendation is the number of the sensor is very limited. How many times that actually you can recommend us to use your sensor? How many times that we can repeat the same, use the same sensor? Because just now you said that if you use the same sensor for many times, it become soft, right? And
Yes.
so basically, what is the limit? Maybe one, two, three, four, five. Maybe you can say any numbers.
Sometimes
Your
it's not a
experience.
constant number lah.
Uh,
For one, there's one sensor I can test it up to 10 times also can, but
oh, okay.
the graph is look like very weird. It got two slope and it's also one of the problem lah. And normally it's work better, which is perform better if the test value is under the 5. I mean, it means that it's only test as many 5 times below 5 times around there.
Or below 5 times. Okay.
Yeah.
And um, how did how did you control when you put the sample on the sensor? I mean, be how you put the sample on the sensor, because I watch your video. Some kinds of you drop the sample on it. Is there any constant parameter to control it? Maybe amount or number of
Uh,
layer,
uh,
or
uh,
how you did it? How you control the sample of salt, sweet that put on your sensor? Because if not mistaken, in your video, there is step to dry the sample, right? So means that you
yes.
take the reading after dry or during wet sample.
I take the reading after is the sensor is dry. For the uh, how the sample drop on the sensor, I use the spoon
Okay.
because is I forgot to bring my disposable pipette and I
Uh,
left it on my the hostel.
okay,
So I
okay.
use the spoon as the to drop the sample.
Uh-huh. And then you dry it. After that, you measure the
Yes. For the
the
second time
okay, okay. And the features used, there are several features that you listed just now. And I'm sorry, I'm still not clear what that T is about. Is it time? That is T equals to 1, T equals to 4. What does it mean? That T, is that the first reading or time, or what is it? That T actually.
is it means the first value of the table in the my demo video also shows some of part of the value resistance values, which means is
Uh-huh.
the first value for the t equals to 1. 10 t
Okay.
equals to 10 is 10 value. Yes.
Okay, okay. All right, all right, all right. Okay.
I think okay, that's all. Thank you.
All right, thank
Okay,
you.
thank you, Dr. Masura.
Thank you, Dr. Masura, Dr. Suhana, and Wei Jian for the presentation. Thank you, everyone, for attending your presentation, right? So we'll end the presentation. We'll give your marks. Don't worry. We are all very nice. Nice lecturer.
Okay.
Marks will be okay one. Don't worry so much. So you can
Yeah.
all prepare for your upcoming final exam. And then,
All right, thank you, Doctor.
okay, I think we are end the session now.
All right. Thank you, everybody.
Thank you.
Thank you, Doctor.
Okay.
All right, thank you, Doctor. Stay safe.
All right.
Thank you so much.
Thank
Thank
you.
you.
Okay, bye-bye.
Bye bye.
All the better. Bye.
Bye.